Welcome to the fourth webinar of EO Africa series, Evapotranspiration from Space. My name is Egor Prikaziuk, and I'm going to be with you this hour and share my knowledge. I hope you can hear me. And well, let's get started. The plan for the upcoming hour is the following. I will explain you the evapotranspiration concept approximately in 5 minutes, then the physics of this process and its drivers, the equations. Unfortunately, it's science, we cannot get rid of that. Then Penman-Monteith equation, then a small demo about Vapour platform or Food and Agriculture Organization, followed by another modeling concept, that is two-source energy balance model. Then again, a small demo of Sen-ET plugin for SNAP, ESA tool for Sentinel Application Platform. And finally, wrap up and question and answer session. I would like to encourage you to put your questions in the question and answer box, not in the main chat, and feel free to do so also during the talk, in between the times that I switch the topics. I will try to answer the questions. With that being said, we are ready to start. In the year 2018, in my second year of PhD, I was conducting a field campaign in potato field. And as a biologist, we measured green death of potato plants. And in June, everything was fine. And we went to the field, the leaves were green and nice. But when we come there to make a second measurement in July, the plants were completely dead. Even though on that picture, you see the leaves are still green, in practice, it was like walking on an eggshell. They were crunchy, and obviously the plant cannot function. Why that happened? Well, there was not enough rainfall, and all the water that had in the soil, that resided in the soil, just evaporated. Wow, this situation is quite extreme, and it can be easily seen on from remote sensing. For example, this is an image of Europe. Here you see Great Britain. Here you see Netherlands, Belgium, part of France. In June, everything was fine and green. In July, everything went dry and yellow. For those of you who are not familiar with European climate, I might say that this is exceptional case. Normally, everything stays green up until summer, up until autumn, when it finally gets yellow and dry. As I said, that was because there was no water to evaporate. If we look at this picture from the point of evaporation, the topic of today's lecture, we just look at the map, we don't see such a big difference. That what was the evaporation rate in the previous Julys, from the year 2000 to the year 2017. Approximately 2.5 millimeters per day, 5 millimeters per day, depending on the area. And in July 2018, the situation was not dramatically different. Maybe here's a little bit. But keep in mind, these are millimeters per day. And in the difference, we can see that 1.5 millimeter per day was missing. What it essentially means, where I'm heading to, it means that farmers in those areas, if they want to get harvest as they used to, they had to add 1 liter of water extra 1.5 liter of water extra to water their plants. And in some places, like even here in Netherlands, where you have a lot of water, it was not enough. At the end, farmers were not allowed to use so much water for irrigation, and the losses of harvest were quite extreme. With this, I would like to show you the added value of evaporation, of evapotranspiration monitoring, how it can actually be used. But now, let's first discuss what it is actually, if you have not familiarized yourself yet. At school, or even in nursery school, they explain that the ecology and the life is a cycle. In this case, it's a water cycle. Water cycle starts from precipitation. It falls on the ground. Let's start here. The cycle starts everywhere, so it started from precipitation. So either snow or rain falls down on the earth. Then it gets to lakes and at the end to the oceans. But what brings it back is evaporation. The only problem that we see here is that we cannot see that. Rain, we see. Snow, we see. But evaporation, the process that happens constantly and is as large as 90%, the vertical movement of water is as large as 90% of all water that we have in the cycle, but it's invisible, which means that we need models to estimate it. Something that we cannot see, doesn't exist, but we say, but that's not true. It exists, and we need some specific tools to be able to estimate it. In principle, you can see there is a difference between evapotranspiration and evaporation. Evaporation, I think, is more colloquial term, and you might be more familiar with it because it's what water does, and you can see that. But evapotranspiration, there's additional process that is referred to length. In general, there is also thought process that is involved here. It's evaporation from interception. So the process itself is very complex. It has open water evaporation. It has soil evaporation. It has intercepted rainfall, which means that the water comes to the leaves and it evaporates back without touching the ground, without becoming open water or soil water. And there is a process, the biological process, transpiration. This I would like to stop more because it's not quite known. You can make an experiment by yourself in your garden or in the park. If you put a bag on the branch of a tree and you seal it, at some time, I think 1 day is enough, you will see that there is a water in the bag. Where it came from, the bag is sealed. It's not from outside. It came from the leaves. This water comes from the plant. In fact, the leaf, if we zoom in, has some pores on its side below. The pores are called stomata, and they release water from the ground. That is what we see in the bag. By the way, if by some chance you will strive for water, this is one of the survival tricks, how to get pure water, drink, is to, if you have the bag with you, of course. How leaves get it? Well, leaves get it from soil, of course. So through roots of a tree, a plant, grass, the water goes up with a capillary rise. This is another experiment you can conduct. You can see how high the water can go up against the gradient. So there's a jar of water and the different paper types. And if you just touch it, you will see that the water goes up. This is the same movement that happens in a tree trunk. And eventually it releases through stomata. that is it. That is the concept of evaporation. Evaporation has three parts: evaporation from open soil and water, intercepted rainfall evaporation, and transpiration from plants. I remind you again, if you have any questions up to now, please send them. Now we go deeper into the process, and we will look into the physics of evaporation. Essentially, it's just a phase change of water. This water as a substance has three phases. It can be solid, such as ice. It can be liquid, such as water that we know, and it can be gaseous, that is we know as vapor. The phase changes are named here from ice to liquid. It goes through melting. Ice and snow, they melt and they form liquid water. Liquid water goes to gas through evaporation, and this is the process we want to estimate. The way backward also exists the condensation. If you breathe on the mirror, you will see the water that was in your respiration. It stays as water drops on a cold obstacles. Then freezing, we see in meter. And there are also, to make the picture complete, sublimation and deposition. So what we have to do to make the phase change from liquid to gas is to destroy hydrogen bonds. So hydrogen bonds are denoted here with these three dots, is their standard chemical notation, which implies that they are not so strong. Normally it's approximately 30 kilocalories. That's very, very little energy. But because there are a lot of them, that's what makes water liquid. That's what takes holds the molecules together. And once this water hydrogen bond is destroyed, the molecule is free to go, is free to leave. You see here in gaseous phase, molecules are completely disconnected, completely free from each other. Another remark that has to be done here for understanding: evaporation is not boiling. Evaporation happens at all temperatures. We do not have to rise the temperature of water to 100 degrees to evaporate it. Evaporation occurs normally at any temperature that molecules are detached. Now, an important number comes in play. To detach molecules from each other in a liter of water or in 1 kilogram of water, we have to spend 2.5 megajoules of energy. So it's 2,500,000 joules of energy. Where can we take this energy from? But this says that water and energy balance are strongly linked. Normally, the energy comes from the sun. To make you better understand how much 2.5 megajoules are, because that's just a number, you can imagine that you have 12 bulbs of 60 watts, and you lit them for 1 hour, and in total, they will produce in 1 hour 2.5 megajoules of energy, a little bit more. Then, what is a kilogram of water? We, at least here in Europe, we don't measure water in kilograms. We sell it usually per liter. And it's exactly 1 liter. 1 kilogram of water is 1 liter of water. And the number is called latent heat of water vaporization, and is denoted as lambda, Greek lambda, or as L. What you saw on the map that I showed in the beginning is that I use millimeters. I said that we need 1.5 millimeters of water extra to irrigate. And then I said it's the same as 1.5 liter. Yes, it is the same. So if we take this bottle of water and we put it into a pool with 1 meter by 1 meter sides, the height of water will be exact 1 millimeter. So if we have this pool and we have our 12 bulbs above it, we leave it for 1 hour and there will be no water in the pool. It will evaporate. That is 2.5 megajoules per kilogram. And of the physical side of the process. I don't see any questions, so I'll just continue further. The next step is to understand the drivers. So, okay, we understood water has hydrogen bonds. We have to destroy the bond. To destroy the bond, we have to apply the energy, that is 2.5 megajoules. Where do we get this energy from? We get this energy from the sun. The sun is the source of energy for our life. You've probably seen this scale of electromagnetic radiation. The sun shines in the region from approximately 200 nanometers to approximately 4,000 nanometers. And only this part we see is called visible light. Why it shines? It shines because it has temperature. But Earth is also not cold object. Earth also has a temperature, and it also emits some radiation, but because it's colder, the radiation that Earth emits is a little bit more to the right of the scale. It's called thermal radiation. It's from approximately 2.5 micrometers or 2,500 nanometers to 50,000 nanometers. Just for you not to get deceived with this interpretation, the energies are of course not equal because sun is much warmer than the Earth. That's why its energy is almost 1 billion times higher than the energy of the Earth. So the energy comes from sun. And what's next? What happens next is it gets back. It gets reflected. Approximately on a sunny day, a summer day at 12 o'clock, or solar noon, somewhere it's 12 o'clock, somewhere it's not. 12, the energy goes in and then bounces back, goes to the atmosphere, goes back. The energy that is emitted by Earth, because it's warm, it bounces back from the clouds. Also, clouds have some temperature. They also emit some energy. So those two parts is called shortwave radiation, the solar energy, long-wave radiation, the Earth energy. And if we take the net, similarly to the net in the salary, so we remove taxes, we remove what is left, the incoming minus outgoing radiation plus incoming minus outgoing long-wave radiation gives us this number, approximately 650 watts per square meter, or 650 joules per second per square meter, or 10 bulbs in a second lit together. In winter, the situation is different. If the Earth is covered by snow, snow reflects much more light. That's why it's white. So the net radiation is quite small, and the temperature is also lower. So the net long-wave radiation is quite small, and normally the energy, net radiation energy that Earth receives is smaller. Here we finally come to remote sensing part of it. Remote sensing, with satellites, sees the Earth's surface and it sees how much light was reflected. That's called reflectivity or albedo. So we can estimate the outgoing shortwave radiation as the portion of incoming radiation with remote sensing. Then the outgoing energy of Earth is determined by Stefan Boltzmann law, which says that the energy emitted is proportional to the square to the force power of the object temperature. And with a little bit of reorganization, we come up to this view of net radiation. Next step. Well, I see a question, so I'd rather answer it right away. Oh, and two questions. According to the figure, there is not input energy in the infrared. Why? There is input energy in infrared, like here, thermal infrared, or maybe I don't understand the question. How you take into account clouds in the estimation of reflected energy? The clouds, well, funny thing, remote sensing assumes a cloud-free atmosphere when it does so. You don't have an image to do so. But of course, clouds are taken into account by climatological models. So the clouds are also white. So the light essentially it travels down, it travels back up. Here is a white cloud, it travels down again, and then it reflects up. So this multiple scattering from the cloud is taken into account in this way. And transmissivity of the atmosphere is estimated. All right. In the chat, there are some questions. Yes, the record videos will be put online afterwards. So live, answer live. Yes. So thank you for the question. So what we got, the energy entered the Earth. It's called net radiation. But as we know from physics, energy cannot be stored. It always changes its forms. Otherwise, if we just receive each second 150 watts of energy, joules of energy, the planet would just burn out at some point. So the energy leaves the Earth again through the so-called energy fluxes. We will see day and night flux. In the day, the sun is shining, the energy comes to the Earth, and then it changes its forms in the way that we can see, because surface gets warmer and the surface warms up the air. That is called sensible heat flux. Because we can sense it, we can feel it. The latent heat flux is when water, hydrogen bonds between water molecules destroy, and the molecules get free, become gas, and they go free to the atmosphere. And of course, the hot top soil level, it not only warms up the air above it, but it warms up the soil below it. It's called ground heat flux. At night, the situation is different because the sun is not shining. The Earth's surface is cold because it doesn't receive any energy. And in turn, air that was warmed up during the day heats up the ground, and the soil that warms up in the day heats up the ground. And those heating also causes evaporation. What you see here in the box is a simple formula that's called energy balance. On the left side, you see net radiation, the energy that reach the Earth. On the right side, you see the energy fluxes, latent heat flux, water evaporation, sensible heat flux, temperature increment, and ground heat flux, temperature of the soil increment. That was it. And now we're coming about the drivers. The drivers are energy, so solar energy is a driver. Now we're coming to the toughest part that the students don't like, the equations. But first of all, I see there are some more questions in the chat. Or not really? Not really. All right. Then I continue further with the equations. My idea, before I go there, is not that you remember the equations or that you, after the webinar, I will ask you type me down it in an email. No, the idea is that you get the point that it's actually what is behind the process. First, we'll look into a sensible heat flux. As I said, yes, sensible heat flux is the energy that warms up the air normally in the daytime, and you are actually able to see that in hot days. You see that the air has some strange patterns, that the poles seem to be bended. You've seen that many times, I think. Now you know what you have seen. You have seen a sensible heat flux. So the energy goes up to the air, and it has to overcome some resistance. It's called aerodynamic resistance, and essentially the heat flux is driven by the difference in temperature. Latent heat flux is driven by humidity, because it's the same exact movement of water from the bottom to the atmosphere. But if the atmosphere, for example, is completely saturated with water, you cannot put more water in the air. It just doesn't accept it. It will condense to rain or to water droplet. You see, the questions are very similar, with the difference, of course, in the driver. It is vapor pressure gradient is the driver, and it is different in the way that not aerodynamic resistance, but also S, the stomata resistance. Remember the back on the branch? This resistance is also taken into account. What I would like to say here is that if we look at it with the concept of love in the middle of that, we will see that we have some parameters that are easily computable. Air density, almost constant. Specific heat of air, almost constant. Aerodynamic resist, okay. Trigonometric constant, also almost constant. Then there are parameters that we can measure or take from weather station, or we can even take it from a mobile phone. This is atmospheric temperature, how temperature developed during the day. It's wind speed. It's relative humidity. I don't know if you have ever seen weather forecasts. They inform about these three parameters all the time. So it's easy to measure. But what is not easy to measure is the surface temperature. The surface temperature is the key in both gradients, and it's not easy to measure. And I will show you, finally, two ways of overcoming this challenge. First, let me answer some questions. Should you consider only the day net radiation or even the night net radiation as well? Normally, the models operate currently on daily basis, so they account for net radiation over 24 hours. Thank you for the question. Some chat questions. Oh, okay. Not really a question. Yes, we will share the link at the end of the presentation for the recording. Penman-Monteith question. Ah, look, we are perfect in time. It's exactly 30 minutes. Very good. Penman-Monteith equation. So you understood the challenge that we face is that we depend on the surface temperature. So let's remove this dependency. Let's try to somehow remove the surface temperature or estimate it, whatever. What Howard Penman did in 1948 and John Monteith followed in 1965 is they removed the dependency of the surface temperature by substituting a saturated vapor pressure by this equation. It's not obvious, I can assume, but it is still mathematically possible. And it was proven in 18th century by Mr. Taylor that any function that we know the equation of can be approximated around some point that we call A, and we take here the air temperature, can be approximated by the value of the function in its point plus derivatives around that point, first derivative, second derivative, etc. And you see that is truly equal because the Taylor series, they converge to a number. And if you calculate the limit, what does it have to do with our case? Well, in our case, saturated vapor pressure is the function of surface temperature, but we can approximate it as a function of air temperature, and air temperature we know. That's what they did, with the only difference that this long formula, we say that it's delta, and function of TA is ES, so saturated vapor pressure of air, not of surface. It was before. You see that ES star was surface pressure. Now it's saturated vapor pressure at air temperature. But if you listen to me very attentively, you might say, this doesn't look like we got rid of surface temperature because we still need it to compute, right? It is here, TS. Wait a second. We also know that there is heat flux, which depends on the surface temperature, exactly at this difference of surface temperature to air temperature. And that heat flux can be computed from net radiation equation. If we take that equation on top and say that Ts minus Ta equals this difference multiplied by Ri divided by rho and Cp, and we put it into this equation, we'll finally get rid of the surface temperature that we don't know, and we will get the equation. I encourage you in the free time to make this exercise and to make sure that you get exactly this equation stated here, the Penman-Monteith equation. What is brilliant about it is that it depends only on climatic variables, so no surface temperature is needed here. And it joins all the drivers for evapotranspiration in one place. First of all, the heat of water vaporization, lambda or L, is here, and the letter L. Solar radiation, net radiation, it is here. The difference between net radiation minus what went to warm up the soil. Air temperature, it's hidden here in saturated vapor pressure. Evaporative demand of the atmosphere, as I said, it's there. And the wind speed is hidden in aerodynamic resistances. So what we got here is the equation where we can compute everything from meteorological data and some knowledge of the surface, but not the knowledge of surface temperature. This approach is now considered the benchmark of Food and Agriculture Organization. It has been reported in the proceedings of 56, paper 56, FAO 56. I will give a link later at the end of the video. This is the baseline for evapotranspiration estimation. It's time for the demo, but it's also time for the questions that disappeared. I think there was 3 questions. Okay. Yes. Well, please ask them still if you're interested, because there was 3 questions I saw. In the meantime, I'm going to show you the interface. if I'm able to stop the presentation. Vapour.apps.fao.org. This is what you're going to see once you enter there. This project was specifically done for Africa and Middle East countries. You don't need to register if you just want to look on the project, on the products, but you have to register if you want to export the data. There are 3 levels of resolution: continental level, 250 meter, national level, 100 meter. I can click and we'll see that there are less areas who participate in this program, and subnational layer, there are small polygons, 30 meters. The data that they have is located here. For example, in layers, you can see what it is and select the layer that you want. For example, now it shows gross biomass water productivity, but we were talking about evapotranspiration, and we can see, for example, actual evapotranspiration and interception, the 3 components I learned about. For the year from 2009 up until the latest year, because it's annual data. You see here the units, millimeters, in this case, millimeters per year. So the equatorial areas have approximately 1,200 millimeters per year. But I have to select it again. So let me select this layer. Why I like so much this portal, because it allows you to process the data on the portal and just export the results. But for that, as I said, you have to log in. I am already logged in to my Vapour. Then I do analysis. I click here in the bottom left corner to analysis. And for example, point time series. I can select the points. Now I just take arbitrary one and I ask for point time series. I select the time period. Let me select from 2015 to now. Actually, it's annual data, so I can select from the very beginning. Place is this point. I run the operation, and at some time, which is in this case should be not too much because it's just 12 images. I will see. Well, let's wait and see what we will see. We will see this actual evapotranspiration interception values in millimeters. So we saw that there were dry years before 2013. Then there was wet year in 2015, and the years afterwards were also relatively wet. 2020 was again kind of dry in that area. This data you can export, download as CSV, open it in Excel, analyze, compare with the neighboring points with the neighboring countries. What is even more interesting to do, I think, because points measurements might depend on the location that you choose, but the area measurements, here you can also make area time series. And I would just select one of the areas I saved, like Congo, and run it, but in this case for one, oh, actually, let's try. It will also work, because the longer the time series, the more difficult to get them. We'll run operation. Okay, there was a problem, probably too long. Or something with my polygon. Normally, you should be able to do that area time series. Let me select the place just by drawing. Yes. Well, it is possible, but you have to try it yourself. what they have, you can see in the catalog in the bottom left. If we look at the water, they have all kinds of annual evapotranspiration and interception, monthly evapotranspiration interception, and decadal 10 days sum. Then individual component, transpiration made by vegetation, evaporation from soil, interception from the leaves, in annual and in decadal form. That was it, what I wanted to show you about Vapour portal. The equations used in that model is Penman-Monteith. Questions? Yes. Is it actual or potential evapotranspiration? Nikki asks. It is actual evapotranspiration that they compute. What would you consider be the main difference of Vapour with climate analysis products such as NASA Power or ERA5 that also have an ET0 product? First of all, it is not ET0, it is ETA, is actual evapotranspiration. And the difference is that ERA5 is model, so it's closed climatological model, which operates inside itself. And this is based on observations of optical and also thermal to constrain soil moisture. From optical remote sensing perspective, how to calculate the ET under cloud cover? No way. If you don't see, you don't see that. But in Penman-Monteith equation, you don't actually have to see anything. You can estimate the reflectance of your grass. It is called albedo. You can try to measure it on the ground, maybe with drone, if you want, and then use it in your equation to continue the study. What is the frequency and delay in production of this data? This is almost near real time. So let me see it now immediately, and maybe we will be able to produce the area map that I wanted. So I go to layers, I select decadal, and it's already available for the decade that started on the 20th of March. So it happened 4 days ago. The decade finished and the data is already here. Well, let me try again. Bad luck. Oh, one question. How can one have access to Vapour platform? You just register there. Normally, let me log out, and then you will see what you normally see. Sign out. If you open this link, it will be in the description on YouTube. You have to sign in here in the right corner, and then you sign in, even with Google if possible, or you sign in with email. Then you provide your data, and they give you access. Before using Vapour data, is there a need to check the quality of the data by checking NDVI? They do quality checks and they remove outliers, of course, but it's always nice to validate if you know what to. But NDVI, I think it will not really help here. Will the 30-meter products be available in other locations? This I'm not sure about, but they are working on it. Yeah, access, I said already. All right, let's go. See more questions. How reliable is Vapour ETA product in considering different used land cover classes? What is the assumption of Vapour in terms of water availability? Water availability, I'll start from the end. Water availability is not assumed. It's estimated from thermal remote sensing. It's a little far from the discussion. You can take a look maybe in what is called ATBD, the algorithm that they use, because they're quite transparent in what they do. So you can see. So the water is estimated from length of temperature. Different land use and cover classes. As far as I know, there is some difference, but the reliability has to be checked locally with some local measurements, of course, of any data set that you work with. Which bands I used to calculate ET? It's not a bands. They just use the albedo product. So basically, as much best as you want. And how do they relate to Penman-Monteith formula? This is outside the webinar, but you may follow our course, and then you will find out eventually. Because yeah, I would like to present still the second approach, which is sounds to me more interesting. So let me stop with. So let me continue with this further. Oh no, not like this. Like that. Too late. So the platform I have shown you. This is how it normally looks like. This is the address. I will send the link in the chats once we finish, and it will be in the description of YouTube video. And now we go to another concept, to two-source energy balance concept that is currently implemented in Sen-ET plugin for Snap that you have had already webinar about. The case is that surface temperature we cannot measure exactly, but what we can measure is land surface temperature, which sounds the same, but it's not the same. Land surface temperature is the radiometric temperature. And when I first heard about these terms like radiometric and aerodynamic temperature, I thought, how many temperatures we can have? It's just on my thermometer. This is not on your thermometer. On your thermometer is aerodynamic temperature. And this temperature is radiometric. So what it has to do with us. You see here bare soil, and you see here the UVO undivided flying object patches, which is irrigated lens that is called pivot irrigation. So there is a machine that moves around this polygon and irrigates it. That's why something can grow there. But here's bare soil, here nothing grows because it's not enough water. Nobody irrigates there. But if we look at it from a land surface temperature perspective, we will see that the bare soil is very, very hot, like 46 degrees. But the irrigated part is only 26 degrees. How it happens? Why it happens? It happens because of evaporation. Evaporation takes the energy that would otherwise warm up the soil, destroys hydrogen bonds that I've talked about, and the molecules leave. But with all this, it creates a cooler environment. But this is the temperature that we measure not with thermometer, but with radiometer, with remote sensing. And we have to relate it to the Stefan Boltzmann law that I told you about in this case. So when this is the temperature of the object that would emit this amount of energy. So it's something closer to, somewhere close to this range because it's still Earth's temperature. For example, this is 15 degrees. And if it's 40 degrees, the peak will be higher and more to the left. If it's 26 degrees, the peak will be somewhere in the middle. What two-source energy balance model does is it decomposes this radiometric temperature, land surface temperature that we see, into aerodynamic temperatures of canopy. C means canopy, vegetation, and S in this case means soil, where FC is the fractional cover, so it's literally the portion of radiation of vegetation that we see and the portion of soil that we see, because what is not vegetation is soil. This decomposition gives us a way to, this measurement of land surface temperature gives us a way to decompose, to guess, first it guessing the temperature of individual components, and then in the iteration, which in case of two source energy balance models, only one iteration, it identifies sensible heat flux of canopy, sensible heat flux of soil. I decided not to put here the formula, but if you want, here it is, the same formula that you have already seen. So this temperature is estimated, and then we check, and then we compute latent heat flux of canopy, that is called transpiration, and latent heat flux of soil, that is called evaporation, as a residual of energy balance. The net radiation that it received, we know from albedo, as I told you. Sensible heat flux of canopy, we can adjust the temperature of both fluxes to satisfy this equation and to actually produce estimates of latent heat flux. And then to make the total evaporation, in this case evapotranspiration of the scene, we sum them together. And what we get after division by lambda is this equation. This is how the plant look like for the modeler. In this case, two source energy balance model, the soil temperature warms up the air, overcoming the surface resistance, soil resistance, and creates sensible heat flux. Leaf has temperature. It also warms up the air, creating a canopy sensible heat flux, and then they join at some point because soil is somewhere near or under the canopy, and they join together. They both overcome aerodynamic resistance, and they heat the air that is above the canopy. These changes in temperature approximated by two source energy balance model can be used to calculate latent heat flux as a residual of energy balance. That was the basic. There will be, I think, no more formulas in this lecture today, but I see there are several questions, so I would like to answer them first, and then I will show you what the plugin does. Okay, anonymous attendee. There are comments answering the reliability of the product. Suggests to read the description of Vapour in reply to the previous question. The difference between radiometric, what is the difference between radiometric temperature from satellite and surface temperature in the sensible heat flux and latent heat flux equations you showed? The difference is that the radiometric temperature is the temperature that you the temperature that needed for heat fluxes is the temperature that you feel. So if this is my surface, if I touch it, the temperature that I feel when I touch it, the skin temperature, is the temperature that we need in the equation. And aerodynamic temperature is a little bit different temperature, is the temperature that the body would have to produce the energy, to emit the energy in accordance to Stefan Boltzmann law. In some models, they are, well, no, they're not assumed the same. They are a little bit different. So I wouldn't like to go too much into details of that. So I think if you suggest to read listener suggests to read about Vapour, I also suggest to read about difference in radiometric and skin temperature. How does TSEB account for evaporation for intercepted rainfall? Is it in the LE of canopy? It might be there, but as far as I know, they are not accounting for that. This is normally thought to be 0.2 millimeters per day, so or 0.02 millimeters per day. So it's tiny contribution, which they don't account for. Otherwise, it would ask to provide precipitation data, and they don't do that. If focusing on some urban heat situation, we might then have to get rid of canopy part. Yes. If you would like to know how to get rid of canopy part, you just don't include transpiration in the model. You assume the surface heat, the soil heat. And then in this case, I think you can simplify and use single source energy balance model, what is called, because this is two source, vegetation and canopy, and there are also single source models for urban heat. Does a canopy temperature occur above the canopy layer? The canopy temperature occurs above the no, canopy temperature is, as I said, is the temperature if you touch the leaf. Well, if you touch all the leaves in the canopy and you average temperature, then this is the temperature of canopy that you would get. So it's not the temperature above is the air temperature, it's the temperature of touch. How can one have access to Vapour platform? I forgot already, you just ask for it, you not log in, sign up in a similar way you sign up for everything else in this world of the internet. So you provide your email, you invent your password, and you want to say organization. I'm not sure about that. Okay, let me see again. Since there are quite a few questions, if I missed something, please, or if you want me to clarify the answer, please send the question again to the question answer box, and because I only see the newest, the latest questions. But to the best of my knowledge, I've answered all of them. Finally, we are getting to the European Space Agency plugin, which is SNAP. And here, instead of 1,000 words, I will just let you watch a 40-second video, and then you will understand everything. I'm not going to comment it, but the video is without. Okay, I'm going to comment it. The video is without sound. So SNAP plugin produces high-resolution evapotranspiration, daily evapotranspiration. If we look on Sentinel-3 image on those two fields, Sentinel-3 image is 1 kilometer resolution. You don't see the fields. You can apply the model, but you don't see the fields. But if you look at Sentinel-2 observations and you do what is called sharpening, you decompose the temperature between different pixels, then you can clearly visualize different patterns of those between those two fields. That is high resolution evapotranspiration with Sen-ET plugin. Here you can also see the date when it happened. So you can technically have all evapotranspiration, daily evapotranspiration. There is one but. It takes some time and skill to apply, and actually to set up. Once it's set up, you can apply it in the batch processing. What you need is a 5 input data sets. First is a Sentinel-3 level 2 image, length of temperature. Sentinel-2 level 2, top of canopy reflectance of Sentinel-2 at 20 meters. Then meteorological data set that was already mentioned in one of the questions, ERA 5 length meteorological data set. It's 10 kilometers, but meteorological data, well, for now cannot, if you don't have weather station, cannot be more precise. And the land cover classification map and digital elevation model. Once you have all these 5, those 2 are normally got by SNAP, but they're still needed for processing. There are 15-step procedure, the main steps of which are the retrieval of biophysical parameters, leaf area index, and vegetation cover, because vegetation cover, fractional cover, is what we use to split the temperatures. Sharpening of land surface temperature from 100 meters, from 1,000 meters, 1 kilometer to 20 meters. Computation of resistances, what we need in these equations, estimation of net radiation that we have to partition also. And finally, we use this iterative optimization for estimation of instantaneous ET. It's very important, by the way. What you see in land surface temperature it's instantaneous. So it is at the time of the satellite overpass. But what we want is a daily ET, and daily temperature changes a lot. So what they do is they upscale from instantaneous value to daily value using evaporative fraction, if I'm not mistaken. I would like now to show you how it looks like again, because this is interesting to see. Let's start. These are some of the products that you may have. This is the interface of SNAP, Sentinel Application Platform of ESA. If you go to tools, optical thematic length processing, Sen-ET, once you installed it, you will have all the steps of the 15 steps I mentioned before. And the first one, you will retrieve leaf array index. This is leaf array index map. This is the range. Now I put it from 0 to 1. You see that this is desert area, and here the river goes. And around the river, there are fields which are green. I can zoom up a little bit. You will see the fields that are irrigated. They are green. They have some leaf area index. Then we go to the land surface temperature, and land surface temperature shows us the same thing, that the land surface temperature of the soil is very high. Land surface temperature of vegetated pixels is very low. And here it's very nice. We use quality flux, so some pixels are discarded, and you see the normal size of the pixel of 1 kilometer pixel is that big, and the resulting image is sharpened. So the resulting land surface temperature is 20-meter resolution. And the daily evapotranspiration, even more quality flux are applied here. So the model does not succeed for every pixel that you have to know. But in the irrigated area, it is July in somewhere in desert area, so temperature is high. It's around 6 millimeters per day, the evaporation here. So 6 bottles of water come from 1 square meter per day. And in desert, mostly it's broken, or there's no evaporation. With that, okay, I see some more questions. So I would like to answer them. I was falling to error while error was while running Sen-ET is segmentation fault. Yes, errors for Sen-ET are inevitable. I was able to run it only on a Windows machine. So the machine that was shown on Linux server, we cannot. I wasn't able to, because what I get is the second error that you mentioned, segmentation fault while calculating fractional gluten. So I did it in Windows, and then there are several steps that you have to do in Windows. ESA CCI, LAN cover and LAN use data. I downloaded it externally because my version of Snap could not fetch it automatically. It fetched NA, fetched no values. So I downloaded it externally. If you're interested, I would send you the link, or you can Google the link, because if you are that far to get segmentation fault, then you probably know how to install it. Either is Python plugin available for Sen-ET? It is Python. It is based on Python, and the Python version, I'm not sure if it can be run outside Snap or not, because it uses still GPT Snappy package, and it uses a graph processing tool. So I'm not sure if it can be run outside Snap, but probably. Are you aware if the Sen-ET masks out desert areas and pens and wetlands? The Monteith products masks out these areas. Here you provide the mask yourself, but as you saw on the example, it masked down, so some quality checks were done, or it was not able to close the energy balance. So it kind of, the result, it masks it out, but you can have some control on that. In Sen-ET, a land cover available for all the surface of the Africa. Yes, ESA CCI is available for all world. In the code behind the Sen-ET plugin, open available. Yes, the code is open and it is available in GitHub of Hector Nieto, the author of the plugin. The link will also follow in the final slides that we have, some two or three slides. What would be the main differences of the Snap implementation with PyDis Alexi? They were very different. I have not used PyDis Alexi, but I know what this Alexi model does. It uses geostationary satellite information and sharpens also sharpens lens of this, not sharpens evaporation on the product. The assumptions behind the model are different. Alexi uses time rate of change to the evolution of lens surface temperature in time, and this is a single snapshot of lens surface temperature. Alexi can do that because it uses geostationary satellites. It's a satellite that looks on the Earth all the time and delivers products each 15 seconds. So you can see the change temperature time, lens surface temperature time. Super nice. Okay. Oh, thank you. There is some, yes, because we are a little bit running over time. So thank you for the answers. Anonymous attendee. How much can aerodynamic resistance affect ET? Very much. If the aerodynamic resistance is high, it is more difficult to get the water up. So it will block the ET will be low. If aerodynamic resistance is 0, the ET, well, technically it will be infinite, but infinite, so the air will pass and evaporate very easily. Can you say a bit more about the validity of Sentinel-2 derived biophysical parameters, particularly the LAI? These are derived by a Snap biophysical processor. Snap biophysical processor. This is which is there. If you go to optical, thermal, and processing biophysical processor, this is processor. It is, as in the topic of evapotranspiration, you of course have to validate any observation with the ground measurements that you have, if you have them. So, but it is quite general because it's based on a radiative transfer model inversion, which is supposed to be general in this respect. Yeah, I see this question. Somehow is sorry. One about access to Vapour platform is, but it's everywhere the same question, I think. How similar is Sen-ET to ET? It is exactly the same thing. The project Sen-ET plugin was developed for, was continued in ET for FAO. Yes, let me summarize what we have discussed today, because we have discussed a lot, so it requires a summary. And then we will continue with the questions. I will be here up until the point you need me. Shift F5. Yes. Yeah, we're a little bit over time, but that's because the question and answer sessions was in between the different subjects. So what I told you about today is evaporation. So it's the rate of water vaporization coming from liquid state to gaseous phase. The process is very important in the water cycle, and it makes clouds, it makes rain, it closes the cycle, if you want. The estimation is important also for practical application, such as irrigation. So it can show you how much to irrigate, how much your crop needs water. And the interesting thing, we cannot see that. We see the rain, but we don't see evaporation. That's why we need models. The models are based on physics, that we need energy to destroy hydrogen bonds and get out of it. The energy comes from sun, and then it's split not only onto changing the phase of water, but also onto warming up the air, which is sensible heat flux. And we need ideally surface temperature to solve it in a blink of an eye. But that measurement we don't have with remote sensing. And we also don't have it without remote sensing. I mean, unless you really measure the soil temperature in every square meter, but it's quite costly. That's why there are two approaches to estimate, about two basic approaches. There are many approaches, but those are two great pillars. One is accepted by Food and Agriculture Organization, it's Penman-Monteith equation, that disables, removes the dependency of unknown surface temperature by Taylor series decomposition. And it uses meteorological parameters available at nearby weather station or global climatological datasets. And remote sensing helps estimating in this formula net radiation through albedo and resistances through leaf area index. Another approach, two-source energy balance approach, it calculates transpiration and evaporation as a residual of energy balance. But the basics of it, which is not written here, unfortunately, but the basic of it is observation of land surface temperature. The timing is a little bit different, but here I summarize the links that you may follow, the papers that you would like to take a look at for further developing your understanding of these concepts. The Penman-Monteith equation is explained very well in FAO irrigation and drainage paper 56. Here's the link. Of course, I will add it in the description because you cannot click it. I also cannot click it here. The Vapour platform, what is behind the model behind it, is explained in on that link on the web page. Two-source energy balance, the model of Norman, Kustas and Humes, is explained in the paper of them of 1995, and the plugging is further explained based on that model, is further explained on the ESA Sen-ET part. Finally, to conclude, I would like to thank you for your attention. And if you would like to know more about this subject, because I saw there were interesting questions that unfortunately I cannot cover now in 1 hour, I invite you to join our community if you are not a member yet of EU Africa Research and Development Community. Once you enter there and register, you could access 2 courses. The open online course that is approximately 30-minute lectures for various topics. For us, this topic is week number 9, evapotranspiration from space, where we discuss those concepts in somewhat more details and illustrate how it can actually be used and how different data sets are comparable against each other, because somebody mentioned how NASA compares to Vapour, how Vapour compares to Moody's. Those cases are in that 30 minutes videos. And then there's bigger course, water and energy budgets from Earth observation. This is already, if I'm not mistaken, 5 weeks, 8 hours per week that uncover the further projects. And then you feel free to repeat this lecture, because I understand that there's a lot of material in 1 hour. And I don't see you all, and I don't see your reactions. So you might want to recap again, and the video will appear soon on YouTube channel. In the big chat, there is a link already shared by Job to that, and you feel free to follow us on Africa. There is one request. I would like to ask you to do me a favor and to fill in the questionnaire, which consists of 5 questions. If you like it or not, if you did not, I will send it to everyone in the chat right now. So if you could fill it in, it would be great for statistics. Then, yeah, here is our platform. Just in case you have not known yet, once you log in, you will be able to see this panel on the right, and the Space Academy is a screenshot that I showed you. Space Academy, you can access the course and register, or you can access the Moodle Cloud and follow the courses in more details. Yeah, this is the questionnaire. 5 questions. Please fill it in. If there is more question, yeah, thank you. It's pretty that anonymous attendee. I don't know who helps me to conduct this webinar, but thanks a lot. If you have further questions, you can also write me. The email was in the beginning of the lecture. Well, with this, I thank you for your attention, and we would like to then close here. Thank you very much.